Okay, so this is a pretty short topic, 1.5 reaction kinetics. Right, we've talked about the Boltzmann curve and how we can use it to explain why lowering activation energy will increase the rate of reaction, as happens with a catalyst, and why increasing the temperature also increases rate. So just a couple of other things which they have asked in the past on the Boltzmann curve. So just draw one here. Right, they have said one thing to notice. This is zero. This is energy and number of particles. The at zero particles. This line passes through the origin, so 0 particles have 0 energy. Okay, that is always the case. And another thing to mention is, even if you've got quite high temperatures, even at a high temperature, there's always a few particles with very low energy. So why is that? It is because so when you have a collision between two particles, the total energy is conserved, but one of them can sort of fly off much faster than the other one and leave the other one almost standing still. Like when you have two snooker balls, sometimes when they collide, and one of them seems to get all of the energy, flies off faster, and one of them stops dead. That's the reason for having a small number of particles, even when the temperature is high, that have got very little energy. Though what I would also do is just a little summary thing here is we think about rate of reaction. Rate of reaction is dependent from the collision theory. Okay, we say so the rate is dependent one on the frequency of collisions, but not just that. It's also dependent on the proportion, the percentage of collisions which are successful. So it's a function of those two things, isn't it? Right. So I'm going to think about all the things that we can do to increase the rate of reaction. So we can increase the temperature. This is GCSE stuff, really, isn't it? We can increase the concentration when we're talking about solutions. We can increase the pressure when we're talking about gases reacting. And that's the same, really, as increasing the concentration of solutions. What else can we do? We can, if it's solids, we can increase the surface area. And finally, we can use a catalyst. So we want to think about how those things affect these two things: the frequency of collisions, we'll put here, frequency of collisions, and here not the frequency, but the percentage of collisions which are successful. All right, so let's do that. Okay, so with right, what increases the temperature then? If you increase the temperature, do you increase the frequency of the collisions? Yes, you do. That goes up. Why? Because they're flying around faster, so they're more likely to collide. And do you increase the proportion which is successful? Yes, you do, because more of them will have energy greater than the activation energy. Let's think about increasing concentration of solutions, right? If you increase the concentration, yeah, the frequency of the collisions will increase, but the particles don't have any more energy, so you'll do the percentage of collisions which are successful will be the same. You'll have more collisions, so you'll have more successful, but the actual proportion in which is successful stays the same. Same for gases. If you increase the frequency of the collisions, if you increase the pressure, yes, you will get more collisions, but there won't be any change in the proportion which is successful. No change. It's just worth mentioning, but it's a common misconception I've seen with some people, and they think that if you increase the pressure of a gas, somehow you increase the energy, the kinetic energy of the particles. You don't. You just like have more of them squashed into a smaller area, but they've got the same. Distribution of energy. Obviously, this one, surface area, yeah, you're going to get more collisions, but no change there. And then catalyst, the interesting one. Well, we know what happens to the proportion of collisions which are successful. We know that increases. Why does it increase? Because the activation energy is lowered. But does it change the frequency of collisions? No, it won't. It won't change them, because it won't change the energy of the particles. So we can see that temperature is the only one that affects, that will do both things, increase the frequency and increase the proportion of collisions which are successful. Because it's not worth doing another video on this, it's going to be a little bit long, but required practical number 3, which is basically a GCSE practical, is you measure the rate of reaction of this reaction. You get sodium thiosulfate, and you add acid to it, hydrochloric acid, and you get sodium chloride solution. You get sulfur dioxide, which is a nasty smelling gas, and you get sulfur solid, so you get particles, and you get water. Right, I can't move that anymore. I can, yeah. Okay. So the let's think about why do we do this one. The reason why you use this, it's very easy to measure the rate of this reaction, because this is a solid. You get a precipitate, it goes cloudy. So if you want to measure the rate of reaction, you get a beaker of your thiosulfate, and you add some HCl to it to start. Okay, and what will happen, you look at it with your eye here. This is your eye, and you put it on a piece of paper with a cross, and you time how long for the cross to disappear. That is required practical 3. And what you do is you keep all the concentrations of thiosulfate the same, and you change the temperature. You change the temperature, and you'd have to incubate this thiosulfate solution in a water bath before you start doing it. And you do a range of temperatures, and you measure how long it takes for the cross to disappear. Now, we need to, with that, the time taken for the cross to disappear is not the rate of reaction, is it? Okay, so the rate of reaction is going to be the mass of sulfur produced over the time. That's what rate is. Okay, rate of product production. So, well, how do we measure the rate here? Well, we're presuming that this is the same. So this remains constant. So you have the same mass each time to obscure the x. Okay, so that we're presuming that. So that number is the same. So that's a constant. So we get from that then rate is proportional to 1 over the time taken. So that's what that's how we're going to measure we'll work out the rate of reaction. Rate is proportional to 1 over the time taken. So what we can say then is we can say that rate, just go back, is equal to any constant over the time. Now that constant really should be the mass of sulfur, but we're not going to work out the mass of sulfur. And quite a lot of people, they will make this equal to 1. So then your rate is going to be saying if you took 20 seconds, rate would be equal to 1 over 20 equal to 0.05 units. It would have to be sort of arbitrary units. And what a lot of people do is, instead of having that as 1, they say let's make rate equal to 1,000, and then it just gives you nicer units. So rate is equal to 1,000 over the time. So instead of having 0.05, you're going to end up with sort of non-decimal numbers, you end up with 50 and so forth. So when you do this experiment, you're going to end up with a series of your results table will look something like, you'll have temperature, degrees C, and you will have time for X to disappear in seconds, and then you'll have rate, which you'll probably work out as 1,000 over the time taken. Right, so you'll end up with a series of results. So you're probably not going to do 0 degrees C because that's a bit tricky. Most solutions, when you get them out at about 20 degrees C, so you could do one with, but using an ice bath, so you could probably do 5, and then you can just do 18, and then you might have done 27, and then 43. You wouldn't try and go for exactly, there's no point trying to go for exactly like 40. You just put it in the water bath for a bit, let it warm up, and then whatever temperature is, measure that and do the experiment. So you're going to get all the different times for these, and then you're going to work out rates. If you plot it on a graph, you won't get a straight line. And we do more on this in the next rates of reaction in 1.9. You'll actually get a curve with an exponential. So this is temperature. So that's rate there. And temperature. So you get something like that. Okay, so that is the end of that topic, but more about rates in section 1.9 in the A level.